In an organic reaction, when reactants react to form a new compound, the reactant that supplies the carbon atom for the formation of a new bond or to the reactant on which the focus is called the substrate, whereas the other reactant in the reaction is called the reagent. In the reaction between chlorine and methane, methane supplies the carbon atom to form chloromethane. Hence, methane is the substrate, and chlorine, the other reactant, is the reagent. Covalent bond between carbon and bromine of methyl bromide gets cleaved and a new bond between carbon and hydroxide ion is formed. The energetics during breaking and forming of bonds, movement of electrons, and the rate of reaction in a sequential description are referred to as the reaction mechanism. Let's study each step in detail. A covalent bond can get cleaved either by homolytic cleavage or by heterolytic cleavage. In homolytic cleavage, a bond breaks equally in such a way that each atom gets one electron of the shared pair. A fishhook or half-headed arrow is used to show the movement of a single electron. Homolytic cleavage results in the formation of neutral atoms or groups with one unpaired electron. These are known as free radicals. The free radicals thus formed are highly reactive due to the presence of unpaired electrons. For example, the homolytic cleavage of the chlorine-chlorine bond in chlorine molecules, induced by heat or light, leads to the formation of two chlorine free radicals. Depending on the number of alkyl groups directly attached to the carbon free radical, alkyl free radicals are classified as primary, secondary, and tertiary. Greater is the number of alkyl groups, greater is the stability. Hence, primary alkyl radicals are the least stable, while tertiary radicals are the most stable. The organic reactions preceded by homolytic fission producing free radicals are called free radical or homopolar or non-polar reactions. Heterolytic cleavage is just the opposite of homolytic cleavage. In heterolytic cleavage, a bond is broken unequally, and the shared electron pair goes to the more electronegative atom. Thus, after heterolytic cleavage, the atom that loses the bonded electrons gets a septet, electronic structure, and acquires a positive charge. For example, in the heterolytic cleavage of bromomethane, the shared electron pair goes to the bromine atom, leading to the formation of a bromide anion and a methyl cation. A positively charged carbon with a septet, which is the methyl cation here, is called a carbocation or a carbonium ion. Carbocations are very reactive as they have a strong tendency to complete their octet. Depending on the number of alkyl groups directly attached to the positively charged carbon, Carbocations are classified as primary, secondary, and tertiary carbocations. For example, ethyl cation is a primary carbocation, while isopropyl carbocation and tert-butyl carbocations are secondary and tertiary carbocations respectively. Stability of the carbocations increases with increase in number of alkyl groups bonded to the carbocation. Hence, primary carbocations are highly unstable, while tertiary carbocations are the most stable. In methyl carbocation, 3 sp2 hybridized carbon orbitals overlap with the 1s orbital of each of the 3 hydrogen atoms. The remaining 2p orbital of carbon is vacant and lies perpendicular to the molecular plane. Therefore, the shape of the carbocation is trigonal planar. There are also heterolytic cleavages where the carbon gets the shared pair of electrons. For example, the removal of the hydrogen ion in the presence of a base from the methyl part of an acetaldehyde molecule leaves both the carbon-hydrogen bond electrons on carbon. Such a chemical species bearing a negative charge on carbon atom and possessing 8 electrons in its valence shell are called carbanions. Carbanions also are classified as primary, secondary, and tertiary carbanions, depending on the number of alkyl groups attached to the negatively charged carbon. Stability of the carbanions decreases with increasing number of alkyl groups bonded to the charge-bearing carbon atom. Hence, tertiary carbanions are highly unstable, while primary carbanions are the most stable. The shape of a carbanion is tetrahedral. All the organic reactions preceded by heterolytic bond cleavage are known as ionic or heteropolar or polar reactions. Polar organic reactions are caused by 2 types of reagents: electrophiles and nucleophiles. Electrophile is an electron-seeking or electron-loving species, as it is electron deficient. Electrophiles may be either positively charged, such as carbocations, hydrogen ion and hydronium ion, or electrically neutral species, such as boron trifluoride, aluminium chloride, ferric chloride, and carbonyl group. A reaction initiated by an electrophile is called an electrophilic reaction. Electrophiles always attack the substrate molecule at the site of maximum electron density. An electron-rich reagent that donates electrons to the positive or electron-deficient site in a compound is called a nucleophile. A nucleophile is a nucleus-loving species, as it is electron-rich. Negatively charged species with lone pairs of electrons, such as hydroxide, chloride, cyanide ions, and carbanions, and molecules such as water, ammonia, and lithium aluminium hydride are some of the neutral nucleophiles. A reaction initiated by a nucleophile is called a nucleophilic reaction. Nucleophiles always attack the substrate molecule at the site of minimum electron density. The movement of an electron pair in organic reactions is denoted by a curved arrow. The curved arrow starts from the point where an electron pair is shifted and ends at the final location where the pair of electrons may move. For example, electron flow from a pi bond to the adjacent bond position, or from a pi bond to the adjacent atom, or from an atom to the adjacent bond position may be represented as follows. You have already learned that most of the attacking reagents carry either a positive or a negative charge. Hence, for a reaction to take place on the substrate, it must possess oppositely charged centers. This is made possible by the partial or complete displacement of the bonding electrons. The factors which influence the electron density in the substrate are inductive effect, resonance effect, electromeric effect, and hyperconjugation. Let's understand each type one by one. In the case of a covalent bond between two atoms of different electronegativity, the electron density shifts more towards the more electronegative atom of the bond. The electron shift polarizes the covalent bond, leading the more electronegative atom to acquire a partial negative and the less electronegative atom to acquire a partial positive charge. The fractional electronic charges in a polar covalent bond are denoted by delta positive and delta negative, and the shift of the electron density is shown by an arrow that points from delta positive to delta negative end of the polar bond. For example, in chloroethane, chlorine is more electronegative than carbon. Hence, the electron pair shared between carbon and chlorine is displaced towards the chlorine atom. Thus, a partial negative charge is acquired by chlorine and a partial positive charge is acquired by carbon. The partial positive charge on C1 draws some electron density towards itself from the adjacent carbon-carbon bond. This causes C2 to acquire a small positive charge. The delta plus represents a relatively smaller positive charge as compared to that on carbon-1. Thus, carbon-chlorine bond induces polarity in the adjacent bonds. Such polarization of a sigma bond caused by the polarization of an adjacent sigma bond is called inductive effect. Inductive effect decreases as the distance from the source atoms increases. The inductive effect is related to the ability of a group to either withdraw or donate electron density to the attached carbon atom of the alkyl group. If any atom or group attracts electrons more strongly than hydrogen, it is classified as electron withdrawing group and is said to have a minus inductive effect. On the other hand, if any atom or group attracts electrons less strongly than hydrogen does, then it is classified as electron donating group and is said to have plus inductive effect. Halogens, nitro, cyano, carboxy and ester groups are electron withdrawing or minus inductive effect groups. Alkyl groups, for example, methyl and ethyl, are electron donating or plus inductive effect groups. Now, let's learn about another important electronic effect called the resonance effect. Resonance refers to the phenomenon where two or more structures can be written for a molecule or an ion. Because of resonance, the electronic charge spreads over the entire molecule and hence affects its polarity. If the polarity of a molecule is developed either by the transfer of electrons between two pi bonds or from a lone pair to a pi bond in conjugation, creating high and low electron density due to resonance, then this phenomenon is called the resonance effect or mesomeric effect, which is designated as R or M effect. Resonance effect is of two types. They are positive resonance effect and negative resonance effect. In the positive resonance effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. Halogens, amino group, hydroxyl group, and methoxy group are some of the examples of positive resonance effect groups. The positive resonance effect in monosubstituted benzene increases the electron density at ortho and para positions. For example, in aniline, due to the conjugation of lone pair of electrons on the nitrogen of the amino group with the pi electrons of benzene, the electron density is increased at the ortho and para positions as shown here. When the electron shift takes place in the direction of the atom or substituent group attached to the conjugated system, it is called the negative resonance effect. Nitro group, cyano group, and carbonyl group are some of the examples of negative resonance effect groups. The negative resonance effect decreases the electron density at ortho and para positions in the molecule. For example, in nitrobenzene, as nitrogen withdraws electron density from the ortho and para positions in the benzene ring, the electron density decreases at those positions as shown here. Now, let us look at the electromeric effect. It is a temporary effect and observed only in organic compounds with multiple bonds in the presence of an attacking reagent. Electromeric effect may be defined as the complete transfer of the shared pair of pi electrons of multiple bonds to one of the atoms in the presence of an attacking reagent. It is important to note that this effect ceases to exist as soon as the attacking reagent is removed from the domain of the reaction. This effect is represented by E, and the shifting of the electrons is shown by curved arrow. There are two types of electromeric effects, positive and negative. In the positive electromeric effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking reagent is bonded. For example, in the addition of acids to alkenes, the pi electrons of the double bond are transferred to that carbon to which the attacking reagent is bonded. On the other hand, when the pi electrons of the multiple bond are transferred to the atom to which the attacking reagent does not get attached, it is called negative electromeric effect. In the addition of cyanide ion to alkenes, the pi electrons of the double bond are transferred to that atom to which attacking reagent does not get attached. Let's learn what hyperconjugation is and how it affects the stability of the various species in detail. A general stabilizing interaction which involves the delocalization of sigma electrons of a CH bond of an alkyl group directly attached to an unsaturated system or to a species with an unshared p orbital, such as carbocations or free radicals, is known as hyperconjugation. hyperconjugation is a permanent effect. Let us take the example of ethyl carbocation to explain this effect. In ethyl cation, the positively charged carbon atom has an empty p orbital. One of the carbon-hydrogen bonds of the methyl group aligns in the same plane with the empty p orbital of the positively charged carbon atom. The electrons of this carbon-hydrogen sigma bond then get delocalized into the empty p orbital as shown here. In carbocations, this delocalization of electrons helps in dispersing the positive charge on the carbocation to the adjacent atoms and stabilizes it. Thus, the carbocation is stabilized by hyperconjugation. Greater the number of alkyl groups attached to a positively charged carbon atom, greater is the hyperconjugation interaction and stabilization of the cation. Hence, the tertiary carbocation in which there are 3 alkyl groups attached to the positive carbon is more stable than a secondary carbocation with 2 alkyl groups. Similarly, a secondary carbocation is more stable than a primary carbocation. Therefore, the order of stability decreases from tertiary carbocation to methyl cation. Hyperconjugation also explains the stability of certain olefins over other halides. For example, propene is more stable than ethene because in propene there are 3 HC hyperconjugated bonds which lead to greater stability. If you observe the resonating structures of propene, you can see that there is no definite bond between the carbon atom of the methyl group and one of the hydrogen atoms. Hence, hyperconjugation is also known as no-bond resonance. Based on the nature of organic compounds and the impurities present in them, organic compounds can be purified using 5 different methods. These are sublimation, crystallization, distillation, differential extraction, and chromatography. In this module, we will look at the first 3 methods. Sublimation technique is used to purify sublimate solid organic compounds. You have learned that sublimation is a process which involves the conversion of a solid directly into vapor without any intermediate liquid state. This process is used for separating sublimable compounds from non-sublimable impurities. In this process, the impure substance is heated in a dish covered with a perforated filter paper over which an inverted funnel is placed. The stem of the funnel is plugged with a little cotton. Vapors of the solid, which sublime, pass through the holes in the filter paper and condense on the cooler walls of the funnel. The non-volatile impurities are left behind in the dish. Iodine, camphor, naphthalene, and benzoic acid are purified by this method. Now let's look at the next method of purification, called crystallization. It is one of the most commonly used techniques for the purification of solid organic compounds. This technique is based on the difference in the solubilities of the compound and the impurities in a suitable solvent. In this process, first, the impure compound is dissolved in a solvent in which the compound to be purified is moderately soluble at room temperature and highly soluble at higher temperature. The solution is heated to get a nearly saturated solution. This saturated solution is then cooled to obtain the compound in its pure crystal form. The crystals are separated out from the filtrate by the filtration technique. The crystals are washed once or twice with small quantities of the pure solvent and dried by pressing between the folds of filter paper and then placed in an air oven. Sometimes impurities impart color to the solution. To remove such impurities, the filtrate is passed through activated charcoal. The charcoal absorbs the impurities. The solution is then filtered and recrystallized as described above. Now let's look at the distillation process. This method is used for separating volatile liquids from non-volatile impurities, and also to separate the liquids which differ in their boiling points. Simple distillation is used when the liquids in the mixture differ appreciably in their boiling points. For example, a mixture of chloroform and aniline, which differ in their boiling point by 123 degrees Celsius, are separated by this technique. In this method, the liquid mixture is taken in a round bottom flask which is fitted to a Liebherr condenser and heated. On heating, the vapors of the liquid with the lower boiling point are formed first, and at a constant temperature, whole of the liquid changes into vapors. The vapors are condensed by using a condenser, and the liquid is collected in a receiver placed at the open end of the condenser. The vapors of the liquid with higher boiling point that are formed later are also condensed, and the liquid is collected separately. Simple distillation cannot be used in the separation of liquids which do not differ much in their boiling points. Another technique called fractional distillation is used to separate liquids which have small difference in their boiling points. In this technique, a fractionating column is fitted over the mouth of the round bottom flask. The purpose of the fractionating column is to increase the area of the cooling surface and to provide hurdles to the ascending vapors. The vapors of a liquid mixture are passed through this column before condensation. As the liquid boils, the more volatile component rises to the top. Some of the condensing liquid obtains heat from the ascending vapors and gets vaporized again, becoming richer in low boiling component. These vapors of low boiling component rise to the top of the column, becoming purer as they reach the top. The pure vapor is passed through the condenser and the liquid is collected in a receiver. The remaining liquid in the distillation flask becomes rich in high boiling component after a series of successive distillations. Each successive condensation and vaporization unit in the fractionating column is called a theoretical plate. The technique of fractional distillation is used in the separation of different fractions of crude oil in the petroleum industry. In the case of liquids with very high boiling points and liquids that decompose below their boiling points or at their boiling points, another method called distillation under reduced pressure is used for purification. In this method, the pressure on the liquids is reduced with the help of a water pump or a vacuum pump. As we know, a liquid starts to boil when its vapor pressure becomes equal to the external pressure. Thus, reducing the pressure on the liquid surface reduces the boiling point of the liquid. In soap industries, glycerol is separated from spent lye using this method. Another distillation process, steam distillation, is used to separate substances that are immiscible with water and steam volatile. That is, get evaporated when steam is passed through them. In this process, the liquid to be distilled is kept in a heated flask and steam from the steam generator is passed through it. The mixture of the steam and the compound is condensed and collected. The compound is separated from water using a separating funnel. In steam distillation, the liquid boils when the sum of the vapor pressures due to the organic liquid and due to water becomes equal to the atmospheric pressure. Since the vapor pressure of organic liquid is lower than the atmospheric pressure, the organic liquid vaporizes at low temperature than its boiling point. Hence, if one of the substances in the mixture is water and the other is a water-insoluble but steam-volatile substance, then the mixture will boil close to but below 373 Kelvin. Aniline is separated by this technique from an aniline water mixture. Differential extraction is a purification technique that is used to separate an organic compound present in an aqueous solution with the help of an organic solvent in which that compound is more soluble than water. The basic requirement of the organic solvent is that it should be immiscible with water so that the organic and water layers can be easily separated. Differential extraction is carried out in a separating funnel. In this method, the aqueous solution of the compound to be extracted is taken in the separating funnel. Then, a suitable organic solvent is added to the funnel. Next, the funnel is shaken for some time and then it is allowed to stand for some time. On standing, the organic compound and the solvent form two separate layers in the funnel. The organic compound, being more soluble in the organic solvent, goes into the organic layer. If the organic solvent is more denser than water, then it goes down and occupies as the lower layer in the separating funnel. The two layers are collected separately by opening the stopcock. The organic substance is recovered from the solvent layer by distillation. If the organic compound is less soluble in the organic solvent, then a technique of continuous extraction is used. In this method, a small quantity of the same solvent is repeatedly used for the extraction of the compound. The solvent layer is collected each time and distilled finally to get the compound. Another important method of identifying, separating, and purifying compounds of a mixture is chromatography. The name chromatography is derived from the Greek word chroma, which means color, and graphein, which means to write. The principle behind this technique is the differential adsorption of various components of a mixture over or on the fixed or removable phase called stationary phase under the influence of moving phase called mobile phase. In this method, the mixture of substances is applied onto a stationary phase, which may be a solid or a liquid, a pure solvent or a mixture of solvents, or a gas as a mobile phase is passed over it. The components of the mixture get gradually distributed between the two phases. Thus, the components in the mixture are separated from one another. Based on the principle involved, chromatography is divided into two types: adsorption chromatography and partition chromatography. Adsorption chromatography is based mainly on the differences between the adsorption affinities of the different compounds in a mixture on the commonly used adsorbents like silica gel and alumina. When the mobile phase is allowed to run over the adsorbent, the components in the mixture move by varying distances over the stationary phase. Based on the principle of differential adsorption, adsorption chromatographic techniques are of two types. They are, namely, column chromatography and thin layer chromatography. In column chromatography, first, the stationary phase, which is the adsorbent, is packed in a vertical glass tube. Then, the mixture of components to be separated is placed on the top of the stationary phase. An appropriate mobile phase or eluent, which is a liquid or a mixture of liquids, is allowed to run down the column slowly. During elution, the components in the mixture get eluted according to their adsorption strengths. The components which are weakly adsorbed are eluted first, and components which are strongly adsorbed are eluted later. Thus, complete separation of the components in the mixture takes place. Now let's look at the thin layer chromatography. Thin layer chromatography involves the separation of substances in a mixture using a glass plate which is coated with an adsorbent. In this method, a thin layer of adsorbent, preferably alumina or silica gel, which acts as the stationary phase, is coated on the glass plate. The plate is known as thin layer chromatography plate or chroma plate. Then, a small spot of the solution of the mixture to be separated is applied about 2 cm above the one end of the glass plate. Then the plate is placed in a closed container containing the eluent. As the eluent moves up the plate, it causes the components of the mixture to distribute between the adsorbent on the plate and the moving solvent, thus separating the components of the mixture. The relative adsorption of each component in the mixture is expressed in terms of its retardation factor, RF. The value of the retardation factor is determined by dividing the distance moved by the substance from the baseline by the distance moved by the solvent from the baseline. The retardation factor of a component is unique with respect to a stationary phase. Hence, any unknown component present in a mixture can be identified with the help of its retardation factor. The components are separated into separate spots, appearing from the bottom to the top of the plate. Depending on the degree of adsorption, the separation of the components takes place and leaves different colored spots when the compounds are colored at different levels of the plate. The spots of the colorless compounds, which are invisible to the eye, can be detected by placing the plate under ultraviolet light. Another method to detect the spots of colorless compounds is by placing the glass plate in a covered jar containing a few crystals of iodine. The colorless spots of the compounds which absorb iodine will appear as brown spots. Apart from these two methods, sometimes an appropriate reagent may also be sprayed on the plate. For example, amino acids are detected by spraying the ninhydrin solution on the glass plate. On spraying ninhydrin, the colorless spots appear mainly as purple or brown colored spots. Another type of chromatography is partition chromatography. This technique is based on continuous differential partitioning of solutes between mobile and stationary phases. It includes paper chromatography, where a special quality paper known as chromatography paper is used. Chromatography paper has water molecules trapped within it, which act as a stationary phase. Now let's take a closer look at the procedure. The chromatography paper is spotted at the base with the solution of the mixture to be separated. Then the paper is suspended in a closed jar containing a suitable solvent or a mixture of solvents. The solvent rises up by capillary action and flows over the spot. Depending on the differential partitioning of the components in the mixture, they get separated with the mobile solvent. Such a paper strip is called a chromatogram. The spots of the separated colored compounds are visible at different heights from the position of the initial spot due to their original color. The spots of the separated colorless compounds may be observed either under ultraviolet light or by spraying an appropriate reagent as done in thin layer chromatography. Carbon and hydrogen are the chief elements present in an organic compound. In addition to these elements, an organic compound may also consist of other elements such as nitrogen, oxygen, sulfur, halogens, phosphorus, and so on. The qualitative analysis helps to detect the presence of these elements present in an organic compound. Let us look at how the elements carbon and hydrogen are detected. First, the given compound is heated with the oxidizing agent cupric oxide. As a result, the elements carbon and hydrogen present in the compound get oxidized to carbon dioxide and water respectively. The products obtained are then passed over anhydrous copper sulfate and bubbled through lime water. We observe that copper sulfate turns blue, whereas lime water turns milky. Anhydrous copper sulfate absorbs moisture and turns blue due to the formation of hydrated copper sulfate, that is, copper sulfate pentahydrate. This indicates the presence of hydrogen. When the carbon dioxide formed in the reaction is passed through lime water, that is, calcium hydroxide, a milky white precipitate is formed due to the formation of calcium carbonate. This indicates the presence of carbon in the given compound. Now, let us look at the detection of other elements such as nitrogen, sulfur, and halogens. The presence of nitrogen, sulfur, and halogens can be detected using Lassigne's test. In Lassigne's test, a small piece of sodium metal is taken into a fusion tube and is heated to red hot. Then, the given compound is added to it in small amounts and the fusion tube is again gently heated to red hot. The red hot tube is then introduced into a mortar containing a few ml of distilled water. The red hot tube is crushed and the mixture is thoroughly grinded with a pestle. The contents are then filtered into a test tube. The filtrate obtained is called sodium fusion extract or Lassigne's extract. This extract is used to detect the other elements such as nitrogen, halogens, and sulfur. During fusion, the elements nitrogen, sulfur, and halogen combine with sodium and are converted to sodium cyanide, sodium sulfide, and sodium halide respectively. In other words, they are converted into their ionic forms. Carbon and nitrogen present in the organic compound react with sodium metal to form sodium cyanide. If sulfur is present in the compound, it is converted to sodium sulfide, whereas the halogen in the compound is converted to respective sodium halide. Now, for the detection of nitrogen, a small amount of sodium fusion extract is boiled with a pinch of solid ferrous sulfate and then acidified with concentrated sulfuric acid. The sodium cyanide reacts with ferrous sulfate to form sodium hexacyanoferrate 2. Ferrous ions are oxidized to ferric ions when heated with concentrated sulfuric acid. These ferric ions react with sodium hexacyanoferrate 2 to produce Prussian blue coloration of ferriferrocyanide, that is, iron 3-hexacyanoferrate 2. The Prussian blue coloration confirms the presence of nitrogen in the organic compound. There are two tests that help us to detect the presence of sulfur using sodium fusion extract. The first test involves the reaction between the sodium fusion extract and lead acetate, whereas the other involves the reaction between sodium fusion extract and alcoholic sodium nitroprusside. In the lead acetate test, sodium fusion extract is first acidified with acetic acid and later lead acetate solution is added to this mixture. This produces a black precipitate of lead sulfide, confirming the presence of sulfur. In the sodium nitroprusside test, the sodium fusion extract is treated with a few ml of alcoholic sodium nitroprusside. If the mixture turns violet, it indicates the presence of sulfur. The violet coloration is due to the formation of sodium thionitroprusside. If nitrogen and sulfur both are present in the organic compound, then on heating the sodium fusion extract with acidified ferrous sulfate solution, a blood red coloration is obtained instead of Persian blue. The blood red coloration is due to the formation of sodium thiocyanate ion 3, thus indicating the presence of both nitrogen and sulfur. In the test for halogens, sodium fusion extract is first boiled with dilute nitric acid. To this solution, a few drops of silver nitrate solution are added. The color of the precipitate indicates the presence of the specific halogen. A white precipitate, soluble in ammonium hydroxide, indicates the presence of chlorine. The white-colored precipitate is due to the formation of silver chloride. If the precipitate is pale yellow and sparingly soluble in ammonium hydroxide, then it indicates the presence of bromine. The yellow-colored precipitate is due to the formation of silver bromide. If the precipitate is yellow and insoluble in ammonium hydroxide, then it shows the presence of iodine. This yellow-colored precipitate is due to the formation of silver iodide. To detect the presence of phosphorus, sodium extract is heated with oxidizing agent sodium peroxide. And then treat it with ammonium molybdate. If a yellow precipitate of ammonium phosphomolybdate is formed, it indicates the presence of phosphorus. In the test for halogens, sodium fusion extract is first boiled with dilute nitric acid. To this solution, a few drops of silver nitrate solution are added. The color of the precipitate indicates the presence of the specific halogen. A white precipitate, soluble in ammonium hydroxide, indicates the presence of chlorine. The white-colored precipitate is due to the formation of silver chloride. If the precipitate is pale yellow and sparingly soluble in ammonium hydroxide, then it indicates the presence of bromine. The yellow-colored precipitate is due to the formation of silver bromide. If the precipitate is yellow and insoluble in ammonium hydroxide, then it shows the presence of iodine. This yellow-colored precipitate is due to the formation of silver iodide. To detect the presence of phosphorus, sodium extract is heated with oxidizing agent sodium peroxide. And then treat it with ammonium molybdate. If a yellow precipitate of ammonium phosphomolybdate is formed, it indicates the presence of phosphorus. First, let us see the method of estimation of carbon and hydrogen in an organic compound. Carbon and hydrogen in the organic compound are estimated by Liebig's method. The apparatus used for this method consists of a combustion tube packed with copper oxide pellets, a platinum or porcelain boat, 2 pre-weighed absorption tubes, and a burner. In this method, a known quantity of the organic compound is placed in the platinum or porcelain boat. The boat is placed in the glass combustion tube packed with copper 2 oxide pellets. One end of the combustion tube is connected to the oxygen supply. and the other side is connected to the two U-shaped absorption tubes. One of the absorption tubes contains anhydrous calcium chloride, while the other contains concentrated potassium hydroxide solution. Now, the combustion tube, along with the boat placed in it, is heated and pure oxygen is passed through it. As a result of combustion, carbon dioxide and water are formed. Water in the mixture is absorbed in U-tube containing anhydrous calcium chloride, and carbon dioxide is absorbed in another U-tube containing concentrated solution of potassium hydroxide. The U-tubes are weighed again after this absorption. The increase in the masses of calcium chloride and potassium hydroxide is calculated to get the amount of carbon dioxide and water in it. From the amount of carbon dioxide and water, the percentage of carbon and hydrogen are calculated. Let the mass of the organic compound taken be m grams, and the mass of the water and carbon dioxide produced be m1 and m2 grams, respectively. We know that 44 grams of carbon dioxide contains 12 grams of carbon. Therefore, the carbon content in m2 grams of carbon dioxide may be calculated as 12 multiplied by m2 divided by 44. Now, m grams of organic compound contain 12 multiplied by m2 divided by 44 and m. Therefore, 100 grams of organic compound would contain 12 multiplied by m2 multiplied by 100 divided by the product of 44 and m. This gives the percentage of carbon present in m grams of the given organic compound. The percentage of hydrogen is also calculated in a similar way. We know that 18 grams of water contains 2 grams of hydrogen. Therefore, m1 grams of water contain 2 multiplied by m1 divided by 18. Now, m grams of organic compound contain 2 multiplied by m1 divided by 18 and m grams. Therefore, 100 grams of organic compound would contain 2 multiplied by m1 multiplied by 100 divided by the product of 18 and m. For the estimation of nitrogen, two methods, the Dumas method and Kjeldahl's method, are used. In Dumas method, a known mass of an organic compound is heated strongly with coarse cupric oxide in an atmosphere of carbon dioxide. Carbon and hydrogen get oxidized to carbon dioxide and water, while the nitrogen present in the organic compound is converted into free nitrogen. A part of the nitrogen may get oxidized into oxides of nitrogen. When passed over a heated copper gauge, these oxides of nitrogen are reduced into free nitrogen again. The mixture produced, which contains carbon dioxide, water, and nitrogen, is collected over an aqueous solution of potassium hydroxide. This solution absorbs the carbon dioxide gas from the mixture, leaving nitrogen behind. This nitrogen is collected in the upper part of the graduated tube. From the volume of this nitrogen collected, the percentage of nitrogen in the compound is calculated. If the mass of the organic compound is m grams, the volume of the nitrogen collected is V1 ml at room temperature of T1 Kelvin. The atmospheric pressure is P and the aqueous tension at T Kelvin is P dash. Then The pressure of nitrogen gas at T Kelvin is atmospheric pressure P minus aqueous tension P dash. Let this be equal to P1. Then, the volume of nitrogen at STP is equal to P1 mm multiplied V1 ml multiplied by 273 Kelvin divided by the product of T1 Kelvin and 760 mm. Let's assume that the resultant volume is VML. As we know, 22,400 ml of nitrogen weigh 28 grams at STP. Therefore, VML nitrogen at STP weighs 28 multiplied by VML divided by 22,400 ml. Nitrogen is also estimated by another method known as the Geldahl's method. The method can be divided into two major stages, namely digestion and distillation. During the digestion stage, the nitrogen present in the organic compound is converted into ammonium sulfate. This is achieved by heating the compound in Geldahl flask with concentrated sulfuric acid in the presence of small amount of copper sulfate. Now, the contents of the flask are cooled and transferred into a distillation flask and heated with concentrated sodium hydroxide to liberate ammonia gas. This is the distillation stage. The ammonia produced in this process is absorbed in a known volume of excess of standard solution of sulfuric acid. Therefore, the amount of ammonia produced can be determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating the unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left after the reaction gives the amount of acid reacted with ammonia. Let's assume that the mass of the organic compound taken is m grams. The volume of sulfuric acid of molarity m taken in the flask is VML. The volume of sodium hydroxide of molarity m used for the neutralization of excess acid is V1 ml. As per the stoichiometric equation, V1 ml of sodium hydroxide of molarity m is equal to V1 by 2 ml of sulfuric acid of molarity m. The volume of the unreacted sulfuric acid of molarity m is equal to V minus V1 by 2 ml. V minus V1 by 2 ml of sulfuric acid of molarity m is equal to 2 multiplied by V minus V1 by 2 ml of ammonia solution of molarity m. From the equation, we get that this is equal to twice the volume of the ammonium solution of molarity m. We know that 1000 ml of 1 molar ammonia solution contains 17 grams of ammonia or 14 grams of nitrogen. Therefore, 2 multiplied by V minus V1 by 2 ml of ammonia solution of molarity m contains 14 multiplied by m multiplied by 2 multiplied by V minus V1 by 2 divided by 1000. Therefore, the percentage of nitrogen is equal to 14 into m into twice V minus V1 by 2 divided by 1000 and multiplied by 100 by m. It is important to note that Geldahl method is not applicable when nitrogen is present in the ring, as well as in nitro and azo compounds. This is because the nitrogen of these compounds does not change to ammonia sulfate under these conditions. Halogens are estimated by Carrier's method. In this method, a known mass of organic compound is to be heated with fuming nitric acid in the presence of silver nitrate in a hard glass tube called Carrier's tube. In this process, carbon and hydrogen are oxidized to carbon dioxide and water, while halogen is converted into silver halide. The halogen forms a precipitate of silver halide. This precipitate is filtered, washed, dried, and then weighed. Let the mass of the compound taken is m grams and the mass of the silver halide formed as m1 grams. 1 mole of silver halide contains 1 mole of halide. Therefore, the mass of halogen in m1 of silver halide is determined by dividing the product of the atomic mass of halogen and m1 by the molecular mass of silver halide. Therefore, the percentage of halogen is equal to the atomic mass of halogen multiplied by m1 multiplied by 100 divided by the product of molecular mass of silver halide and m. To estimate sulfur present in the given organic compound, a known mass of the organic compound is taken in a Carrier's tube and heated with sodium peroxide or fuming nitric acid. The sulfur present in the compound is oxidized to sulfuric acid. The acid is cooled and treated with excess of aqueous barium chloride solution. It gives a precipitate of barium sulfate. This precipitate is filtered, washed, dried, and then weighed for analysis. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of the organic compound taken be m grams. The mass of barium sulfate formed is m1 grams. We know that the molecular mass of barium sulfate is 233 grams. And the amount of sulfur in 1 mole of barium sulfate is 32 grams. Therefore, the mass of sulfur in m1 gram of barium sulfate is m1 multiplied by 32 divided by 233. Therefore, the percentage of sulfur in the compound is 32 multiplied by m1 multiplied by 100 divided by 233 multiplied by m. The quantitative analysis of phosphorus in the given organic compound is done by heating a known mass of organic compound with fuming nitric acid in a Carrier's tube. As a result, phosphorus is oxidized to phosphoric acid. When this phosphoric acid is treated with ammonia and ammonium molybdate, a precipitate of ammonium phosphomolybdate is formed. Sometimes, phosphoric acid is precipitated by adding magnesium mixture. Magnesium mixture is obtained by dissolving 100 grams of magnesium chloride hexahydrate and 100 grams of ammonium chloride in water. To this, 50 ml of ammonium hydroxide is added and the solution is diluted to 1000 ml. On adding magnesium mixture to phosphoric acid, a precipitate of magnesium ammonium phosphate is formed. This precipitate is filtered, washed, dried, and then ignited to produce magnesium pyrophosphate. From the weight of magnesium pyrophosphate, weight of phosphorus can be estimated. Let the mass of the organic compound taken be m grams, and the mass of ammonium phosphomolybdate Bm1 grams. The molecular mass of ammonium phosphomolybdate is 1877 grams. Atomic mass of phosphorus is equal to 31 grams. Therefore, the percentage of phosphorus present in the compound is M1 multiplied by 31 multiplied by 100 divided by the product of 1877 and M. If phosphorus is estimated as magnesium pyrophosphate, then the percentage of phosphorus is equal to 62 multiplied by M1 multiplied by 100 divided by the product of 222 and M. Here, M is the mass of the organic compound taken. M1 is the mass of magnesium pyrophosphate formed. 222 is the molar mass of magnesium pyrophosphate and 62 is the mass of two phosphorus atoms present in magnesium pyrophosphate. For the quantitative analysis of oxygen in an organic compound, a known weight of the organic compound is heated in a stream of nitrogen gas. As a result, the organic compound gets decomposed. Then, the oxygen-containing mixture is passed over red-hot coke, where all the oxygen is converted to carbon monoxide according to the equation shown. This gaseous mixture is passed through warm iodine pentoxide when carbon monoxide is oxidized to carbon dioxide, producing iodine. This reaction may be represented as shown here. To make the amount of carbon monoxide produced in the first equation equal to the amount of carbon monoxide used in the second equation, multiply the first and second equation with 5 and 2 respectively. It is clearly evident from the equation that 1 mole of oxygen liberated from the compound produces 2 moles of carbon dioxide. Thus, 88 grams of carbon dioxide is obtained if 32 grams of oxygen is liberated. Let the mass of the organic compound taken be m grams. Mass of carbon dioxide produced be m1 grams. We have seen that 88 grams of carbon dioxide is obtained if 32 grams of oxygen is liberated, and then m1 grams of carbon dioxide is obtained if 32 into m1 divided by 88 grams of oxygen is liberated. Therefore, the amount of oxygen liberated from m grams of organic compound is equal to 32 into m1 divided by 88 multiplied by m.